Welcome to the first lecture for Calculus 2, and we're on section 5.1, so let's get started. We're looking at the connection between two things that might not seem connected right away, which are areas and distances. So let's consider a graph, and I've already got axes set up, so let's think about maybe a car or something driving. So this graph is going to be the velocity of the car. So it probably starts with a velocity of 0, and then it speeds up and goes faster, and then maybe it slows down for a little while and then goes faster again. Okay, just making that up. But this is presumably time along the bottom, probably in hours. We'll get time there and say this is like 1 hour, 2 hours, 3, 4, 5. And the question is going to be how far, what's the distance that this car went when all we have is the graph of velocity. So if this car had a constant velocity, keep in mind this is an algebra problem then, and there's a little formula that says distance is rate times time. So if you know you're going, 50 miles an hour for 5 hours, you just multiply them and get 250 miles for your distance. This is a little more complicated though, because we are not going at constant velocity. So there's no just one rate that we can multiply by. But let's, and actually I think this is going to go a little bit better if we have a graph paper behind this. So let's throw that in there. And let's say that maybe this is, let's get, say this is 50 miles an hour. Let's say this is 100 miles an hour. This is a very fast car. It gets up to 120 right here. But anyway, let's simplify our work by assuming that for the first hour, he's not going all these changing speeds, but he's just going the speed at the end of that first hour. So let's say at 1 hour, the function value, the velocity seems to be what, about 110, 112 there, maybe? So let's say for the first hour, he's gone 112 miles an hour for the entire hour. So there's my rate times my time. And the distance then would be 112 under that assumption. Let's do the same thing for the second hour. Let's assume that he's going, actually it looks like almost exactly the same speed at the end of the second hour. Looks like about 112 miles an hour there as well. So let's assume for the entire second hour, he's going 112 miles per hour and does that for an hour also. So there's another assumed 112 miles. Notice over the first hour, most of the time the car is going slower than 112 miles an hour. So over the first hour, this 112 is probably an overestimate. And over the second hour, most of the time the car is going faster. So my assumption there is probably too low. Same way after the third hour, this looks like about 70, maybe 72 miles an hour right there. So let's say for the third hour, just assume he's going 72 miles an hour the whole time. Which gives you the assumption that he's gone 72 miles that hour. And the fourth hour likewise is about 60. So let's say 60 miles an hour for 1 hour. And we're stopping at the fifth hour, and that looks like our assumption there is going to be 100 miles per hour. Also for 1 hour, so 100 miles. So with this really rough estimate, we could add these up and just get a rough estimate of how far the car has gone. Let's see, that's going to be 224, 296, 356, 456. Hopefully I did that right. You can grab your calculator and find out if I made arithmetic errors, but that's a rough estimate. So there's a little bit about distances. Also like to point out that we have a connection here between distance and area. So notice this calculation we did for the first hour. This one that we did right here. We said that was a multiplication. It was 112, which was this green height right here, the function value. And then multiplied it by the 1 hour, which on the graph is right here. It's the time elapsed. And multiplying those two together gave us our distance. Multiplying those two together also gives us the area of a rectangle that looks about like that. All right, so this rectangle I'm shading in right now is literally a 1 by 112 rectangle. And I can construct similar rectangles for all of my other distances. All right, the second hour, we're assuming 112 again. And the bottom or top of that rectangle is also a span of 1 hour. So that's rectangle's also a 1 by 112. The third hour, we were assuming like a 72, so the top of the rectangle goes about right there. Bottom's there. And there's a 1 by 72, so an area of 72. And this one, the fourth one, we were assuming 60. And notice when I draw the top of that rectangle, it kind of cuts through the function, but that's all right. That's still the assumption we made, was that it was a 1 by 60, which matched our 60 times 1 calculation over here, and the last one is 100 times 1. So each of these rectangles match one of the distances that we calculated over here. This is a very rough estimate because you'll notice that there's places where the triangle has a huge amount of overage, like right here during the first hour, like all this, all that is wrong, right? That's too much. And there's places where the triangle's not big enough, like this is an underage, if that's a word. Right there, and so is that all this blue that I'm shading in is error. All right. So there's ways, hopefully, that we could make this a little more accurate. And this being calculus, you know, the beauty of calculus is we can make things infinitely small and do infinitely many of them. So really the thing that we're going to want to do is to make smaller rectangles. Really, I could go back and instead of waiting an entire hour before I chopped this off and did a rectangle, I could do a rectangle just for the first fifth of an hour, just using the grid here, and say, let's just check the speed right there, and then check it right there, and then check it right there. Obviously, I'm going to have to add up a lot more rectangles over the first 5 hours now, but notice as I top each rectangle off and use it to calculate speed, there's much less error in these rectangles. So your homework's going to ask you to estimate distances, also known as areas of rectangles, by making bigger green rectangles and then by making smaller, more accurate, and more work yellow rectangles. And eventually we are going to get the power of calculus on our side to do infinitely skinny rectangles and infinitely many of them, and we will have the true distance that the car has traveled, also known as the true area under the curve. But this is a start, and we'll build on it from here.